Hello, myself Arshadati, and today I will perform week 2 experiment of EEC lab. This is our Wheatstone bridge. This is R1, R2, R3 and R4. Each resistors are of nearly 100 kilo ohms. So now we use ADLM kit 1000 to supply 2.5 volt voltage. You can see that nearly 2.5 volt voltage is supplied. Now we will measure the voltage between point A and B. Now we can see that the voltage between point A and B is 0 as it is a balanced V-stone. Now the voltage between node A we can measure. You can see voltage at node A is 1.17. Now at node B, this is also nearly same 1.18. Now we have calculated the VA and VB. As you can see, VA calculated VA is 1.25 and calculated VB is 1.25. And we measured VA measured is 1.17 and VB measured is 1.18. And this is nearly same, and this slightly difference is because of the manufacturing defect of resistors. As these resistors are not properly of 100 kilo ohm. Now we have to provide an input of AC plus DC voltage, as you see 2.5 plus 1 sine omega t. By providing a 2.5 volt to 1 sine omega t, by adding this, the sinusoid voltage will shift upward by 2.5 volt. Now the maximum excitation is 2.5 plus 1, that is 3.5 volt, and minimum is 2.5 minus 1, which is 1.5 volt. Now we provide a sinusoid voltage of AC plus DC through Adam 1000 kit. In this bi-channel I provide input, this is our ground, and bi-channel B I record the output. So now I will set the maximum voltage to 3.5 and minimum to 1.5. Now as we see, the output voltage is somewhere between 1.75 and 1.15. Now we will see the output at VB. This is the output at VA. Now this is our output at VB. This is also nearly same. So this is my Wheatstone bridge, which I make using two 10 kilo ohm resistor and 100 kilo ohm and one 1 kilo ohm. So this is R1 of 10 kilo ohm. This is R4 of 10 kilo ohm. This is R2 of 1 kilo ohm, and this is R3 of 100 kilo ohm. Now let's check this is a ideal Wheatstone bridge or not. So you can see that I have supplied a 2.5 volt voltage using Adam 1000 kit. Now the voltage at point B is 0.022 and at point A is 0.021, nearly same. And the voltage between point A and B is 0. The voltage between point A and B is 0, hence it is an ideal Wheatstone bridge. Okay, so now we have connected 1 kilo ohm resistor series with R1 and 1 kilo ohm resistor series with R4 and supply a 2.5 volt voltage using Adam 1000 kit. And now we measure the VA and VB using multimeter. So VA is VA is 0.2045, 0.204, and VB is 0.244. Now we have calculated the VA and VB of the circuit as shown in the figure, and the calculated VA is 0.21 volt and VB is 0.24, and measured VA is 0.204 and VB is 0.244. Hence these are nearly same, hence proved. Now if we compare this circuit with the previous Wheatstone bridge, we can conclude that previous Wheatstone bridge is the proper Wheatstone bridge, where V output means voltage between point A and point B is 0, but in this Wheatstone bridge it is not. This circuit is not a proper Wheatstone bridge because R1 by R2 is not equal to R3 by R4. Now we have connected a 100 nanofarad capacitor to remove the AC unwanted to this circuit. Now we provide the input of a AC plus DC voltage by channel A and measure the output by channel B. Okay, so this is our output by providing a DC plus AC voltage. Okay, so now we have calculated the Kelvin equivalent resistor of the circuit across point A and point B, and R Kelvin is equal to 10.83 kilo ohm, and also calculated the corner frequency, and the corner frequency is 147.04 Hz. As you can see, now we have made R Kelvin 10.77 connected with a 100 nanofarad capacitor. Now we provide DC plus AC voltage, which we have provided earlier. We provide input by channel A and measure the output by channel B, and this is our ground. So this is our output of the output in which we have provided DC plus AC voltage. Now we will this output is at 1000 Hz frequency. Now we take the reading at different frequencies and plot a graph. As you can see, we have measured the V out at different frequencies, starting from 1 Hz to 1000 Hz, and plot a graph, and our graph look like this, and our corner frequency is nearly about 147, and we can see that nearly at 150 we measured a drastic drop.